So you can hear my voice, right? So,
Yes.
So there is a quick look into pencil code modules. These are like density and hydro modules I will talk about today. So these are very fundamental modules to the pencil code, and these are some of the descriptions about the pencil code. By this time, you obviously know these points. So pencil code is a higher order finite difference code and is highly modular and cache efficient. We got to know about many things about cache efficiency from Philip's lecture. And regarding science cases, so there are provision to use static, uniform and non-uniform grids like Cartesian, cylindrical, spherical, hyperbolic like sine hyperbolic or logarithmic. And there are many more, but all they are static. We are not dealing with this adaptive mesh refinement for the time being. And there are also these non-ideal effects like you can mention, you can use explicit viscosity, resistivity in your code, even different other transport coefficients like heat conductions. And there are also this inclusion of Lagrangian particles. Those Lagrangian particles could be like massless, massive, charged particle. So most of this Lagrangian particle part will be covered by Dhruvaditya. So in on Monday, I guess. So here I can give you a brief overview now. So we'll talk about this density module, which is there in the SRC directory as named as density.f90. So this is the basic equation. So you all know about this equation is a continuity equation for the density, and here rho is the density, u is the velocity field. So this is the equation, and the second equation is just as second equation is exactly the equation number one, but written inside a slightly different format. And you can see here that in the second equation, we are actually checking the time evolution of the log of the density, but not the density. So we actually solve this equation for the log of the density or log rho in the pencil code. So there are a specific reason for that, because in some of the numerical codes, it has been shown that due to numerical issues, rho can be negative for some time. So it is not a physical thing, it is a completely numerical error. So for that reason, we use ln rho, which doesn't allow to get those kind of errors. So this is one difference with other codes, I would say. So this is the equation, and on top of that, here you can use different explicit diffusions like this first one. This is this Laplacian kind of diffusion. This is a physical diffusion. D is your diffusion parameter. It could be constant. It could be your or some variable dependent parameter also. So this diffusion parameters are already coded in the pencil code, so one can look into that. And the second is this upwind derivative. So as Axel was saying that he used this upwind derivative, and many others use also upwind derivative to avoid wiggles in the density profile. But the caution part is that that one has to check whether these upwind derivative schemes are actually affecting your physical realizations or not. Physical realization in terms of like some physical quantities. So this upwind derivative part is also there in the pencil code. And on top of that, you have inclusion of hyperdiffusions. So hyperdiffusions has like purely numerical origin. So they are there to actually make the code stable. So this D3 is actually showing you this actually sixth order hyperdiffusion scheme. So if D3 is your parameter, this hyperdiffusion parameter, if it is constant, you can take out of this out of this bracket, and then it will be like del 6 operation on ln rho. Okay, So del 6 you can think of like in k space it will be like k to the power 6. So that means it will act on these those regions where k is very large. So k is very large means in small scale it will act much more. In larger scale or k small regions it will not act much. So your this Nyquist frequency level, in those levels this hyperdiffusion terms will act and uh, just diffuse some numerical instabilities, and it will actually stabilize your code. So depending on your physics problem, you can use these different schemes like explicit diffusion, hyperdiffusion, and others. Yeah. So some more details. So this is your like setting up your own input files. So when you are setting up your own this physics problem, so first if you want to solve this density evolution equation, you have to set first this in the makefile dot local. I should write that makefile dot local. So here it is written in makefile dot local. You have to say density equals to density, because by default it is written as it density equals to no density. So density equals to density means density is actually checking for a file called density.f9. So .f9 is not written here. So you have to set first this as in the makefile.local to use this density.f90 file. And then you have to set, so this is the general workflow. Then you have to set some initial condition parameters to start.in according for this density.f90 file, and some run and to run this this setup you have to set different parameters in that run.in file also. So symbolically, so what so here it is written in this run.in, you have to set parameters in this density run parts. So if you can check one of the samples, there are these start.in and run.in files. You will get to know, you'll get that hint at what I'm talking about. So this is so in these two pictures what I'm showing you, these are the various available options in this density init parse and density run parse. So density init parse will talk about will deals with your initial condition file, where you can mention various parameters. So I'll discuss them in a moment. Yeah, let's say if you want to start your setup as a like where the density is like a completely you are trying to deal with like fluctuations, like Gaussian fluctuations. So you have to set this init ln row equals to Gaussian noise in your start.in file. So whatever I have written in this typesetting format, they are actually like command for your command for this setup. You can check it exactly copying this part, this text, and you can check in the source code what does it mean. And if you want to use like any sinusoidal function or jump profile, so these are like typical options. So there are, you can find it if one time you can just search it with this kind of strings, you can find many other options which are available there, like sinusoidal, jump profile, I have mentioned it here. Or you can also mention, you can also give input to this your physics problem as like if you just mention like this. So if you want to use a stratification for the density, where density is changing with height, and you want to give this stratification file as an input to your code, that it will at the initial time it will start with that density profile, and then code will evolve with other parameters. So you can use this kind of external .dat or ASCII files to give input as density profiles. So this is about this initial condition for the density, and there are other diffusion schemes of what I was talking about. So if you want to use this explicit diffusion scheme, which is like Laplacian, so you have to use this IDF equals to normal. So IDF equals to normal. So again, this is like a command to use this scheme. So you can just check by copying this and search it in the source file. particularly in the density.f95. And you can see that it is actually solving this equation, it is actually solving conservation equation incorporating this term. So there are many different diffusion parameters are already coded there. You can just explore those. So this is, I was talking about, this is the explicit diffusion part. And as I have already told about this numerical stability, you can set this hyper diffusion term by just setting this IDF equals to diff rho hyper 3. It will automatically take care of this term. So it will incorporate this term, this sixth order derivative term in your density, in your continuity equation, and it will evolve it that way. But this is not the this is not the end. So as you have just setting this diff rho equals to hyper 3, you are selecting this, but you have not actually given this exact parameter value. So I didn't give this D3 value, right? Which is the diffusion parameter, or D value. This is the physical explicit diffusion parameter. So that's why I said here that do not forget to mention the parameter values. Otherwise, it will take default ones. So default ones are like 0. So whenever you are using this scheme, you are saying code that please use this part as in your continuity equation, but the diffusion parameter is 0. So that means this term is giving no input to that continuity equation. So it will put an error. So for that, you have to check the output file, and you will see that code will be crashed and saying a warning that your diffusion parameter is set still 0, but you are using this diffusion scheme. So that's why I just mentioned this in this below part. Yeah. So yeah, the next part is like, if you, in your problem you are dealing with shocks, you have to set, you can set actually this shock diffusion explicitly, which is like the tag is like diff rho shock. The command is diff rho shock. So what it will do, it will not actually, so this diffusion will not actually act globally in your domain or your setup. It will locate these shock profiles where these compressions are like really large, and only on those locations this shock diffusion will act. So it will not actually diffusing your global picture, but where it is required to make the code stable, it will use on those regions. So you can check, the best part to check is that the source code, but before that, you can check the pencil code manual also. So yeah. And these are like typical boundary condition and diagnostics tool. So the default boundary conditions are like periodic for every direction, but one can set this symmetric, anti-symmetric, open for outflows, fixed for fixed temperature according to their physics problem. And to understand the code better, not to use as a black box, so one can set this IP less than 14. So IP equals to 14 is like you will get much less output from the code itself. So code, this pencil code has many comments. It is written in, it can write many comments. What you are actually solving, what values it is taking by default. But if you just set this IP value less than 14, by default it will take most probably it will take 14. But if you just set this IP value to less than 14, like 9 or 10, it will show you many comments that what physics is going on, what you are actually solving, to understand your code better. So that's why I said, like, if, you can set this IP less than 14 for verbose output from this run.out file. So run.out file is actually output file for your run. Corresponding to your run.in executable file. So whatever you put there in run.in file, so for every physics part, there will be comment in run.out file. So one should check those comments in the run.out file to understand their setup much more. So, and different diagnostics tools are also available, like a 0D, 1D, 2D. So one can put one can mention in the code, particularly in print.in, that what kind of this is a particularly useful for these 0D outputs. That if you want to, let's say, if you want to know, understand that at every time I want to know what is my minimum density profile or minimum density value in your domain. So let's say for your physics requirement is that you can't let the density to fall below a certain number. So you can check at every time that what is your minimum density value or what is your maximum density value. So these are like 0D parameters. You can put it in the print.in file, and it will readily give you the output in the time series.dat file or run.out file. Okay, so this is like 0D diagnostics files. There are like some averaging files are also there, which is like 1D or 2D files. Let's say you are dealing with a magnetic field. Say you are dealing with some magnetic field, and you want to see that how how the structures look like if I just do a phi average or radial average. So this could give profile something like this. So here it is for the density only, but there are these variables where you can see different slices. Like so slices will be a 2D diagnostics. 1D diagnostics will be like some directionally variable some parameters, like what I said, this ln rho m phi. So here it is means in phi direction it is only doing the average. So at every for every radial point it will give you the density profile. So these options are there to understand your code much better, or to get to understand your code better. So this is one part, and the last one is this this DTD part. So I'm showing you just an example here. So DTD is actually what is giving you is the relative diffusion time scale with respect to code time scale. So let's say you are allowing your code to take the time step as adaptively. So you want to understand, right, what is the diffusion time scale and what is the ratio with your diffusion time scale and your coding time scale, what the adaptive time scale it is code is taking. So to understand better, or like some troubleshooting thing, you can check this variable files in your pin.in or in the slides files. So now I'm going towards this hydro module, which is this hydro.f90. So you can find it under this source file src. So the basic equation is this. So this is simply the Newton's second law for continuum medium, like for without magnetic field, it will be like just just fluid, and in presence of magnetic field, it will be like plasma. So therefore, I am just writing this basic equation, and on top of that, I am using this S. S is like different sources you can add. The simplest one, I am saying that you can use this gravity, which could be like constant gravity or radially dependent gravity. So you can set, first you have to set this gravity equals to gravity simple in your makefile.local. Then you can set your parameters in start.in and run.in files, as I have said earlier. Now, if you want to use the self-gravity terms, so whatever I am saying here, it is corresponding to different source terms to the Navier-Stokes equation. Or I should say here, particularly the Euler equation here. So self-gravity term you can add, which is like minus grad phi. You have to first turn on this module. You have to include this module in your makefile.local, that self-gravity equals to self-gravity. Otherwise, there by default here it is written as it will use no self-gravity module. There is also that module, you can just look at it. By default, there is no self-gravity. So which if you just include this self-gravity part, it ultimately solves this Poisson's equation. So from density module, it will ask for the rho, this density, and it will solve this del square phi as a Poisson equation, and then it will update here as a self-gravity term to the Euler equation. One can add also Coriolis force. So Coriolis force is here. So by default, Coriolis force is on, but omega is by default it is set to 0. So if one wants to use it, one can set this omega to some non-zero value to use it. Even centrifugal term one can use it, but there are some limitations. So you have to check what comments are coming from the code. To understand better that what you are doing and what code is actually doing, what you want to get from the code and what code is actually doing. If you want to use this Lorentz force star, so then you have to set this magnetic equals to magnetic, because by default it is like hydro. So you have to set this. There are also different terms like viscous force you can add. You can add also some external driving like helical driving or sinusoidal driving. I guess you can explore these things a bit with your own now. So again, you have to set this hydro equals to hydro in makefile.local to use this hydro.f90 or to evolve your velocity field according to your physics problem. And here the two pictures are actually showing you these various input parameters which are available by default in the pencil code. That these are the input parameters and these are the run parameters which one can set. So just again, similarly, I'm showing you that one can set this initial velocity file like this Gaussian noise. If you just set this init u equals to Gaussian noise, again, whatever it is in this typesetting font, one can just copy this and try to check from the code that what is written there. One can also use parabolic profile or sinusoidal, all like linear shear profile to initiate their code. So there are many options. One should, if one is anyone is interested, they can look into those part of the code. And again, don't forget to mention that parameter related to selected velocity profile. Like if you are saying this, you want to use this init this Gaussian noise in as your input velocity, as your initial velocity, you have to say, right, at how much strength you need this Gaussian noise, right? So those are the parameters you have to also mention. Otherwise, it will show you some error that by default it is taking some zero values maybe. Even you can put external velocity profile from maybe getting from some analytical function to your code like this init uu, and you have to mention that the name of this ASCII or binary file. And again, there are also these different explicit schemes for the diffusion to handle the diffusion. There are this kinematic, dynamic, viscosity. So here I'll describe it much more. So this is the typical viscous term pencil code solves, but one can set up to what kind of physics, up to their physics requirement, they can set that what amount of complexity they need. You see there are like these three different terms are there. This is the kinematic viscosity, this is the density, this is the rate of strain tensor. Okay, so if you are not dealing with very compressible fluid, you can just say that there is some options like IVs equals to nu simple. It will just add the viscous force as nu del square u, again a Laplacian. But here it is not a single Laplacian. Here are other terms also, like incorporating this density gradient and this viscosity gradient. So this is one part. And again, here are also different options, like if you just choose new constant, then new will be always constant. One can set also dynamic viscosity as constant. Those options are there. One can choose density, this viscosity, which has like some profile, like tan hyperbolic profile or like sine hyperbolic profile. Those options are there. And if one wants to use this nu as like some temperature dependent parameter following the Spitzer coefficients, those options are also there. So I'm trying to give you a bird's eye view that what you can do, what you can't, or some what are those options are available by default. For numerical stability, one can use this again diffro hyper 3, which is like sixth order derivative of the velocity field. And if you have again shock in your in your physics problem, you can use here. It will be not diffro, sorry, it will be like some diff uu or something underscore shock, which actually only works on the shock regions. So basically what I am to mention here, that with using this diffro hyper 3 or this will be like velocity for diff new hyper 3 or diff new hyper 3 or new shock. So those are actually giving you much more stability in terms of numerically. So they will most probably not hamper your physics problem at larger scale or smaller k value, but it will stabilize your code by diffusing some small scale instabilities at larger k value or smaller spatial value. Okay, so with this parameter, if you set these parameters, these will actually help you to work in much higher Reynolds number. But one disclaimer is that you have to check that using these diffusion parameters, how your original physics problem is altered, whether it is how it is completely altered or how much it is, that you have to check, and that is also problem dependent. So just one plot here. This is the velocity profile what I got from the pencil code manual, and you see here this previous this checkers board like structures. So maybe in this code or in this setup, they are using this diffusion or hyper diffusion parameter very small. So one can increase that hyper diffusion parameter and see whether they are getting so whether still they are getting these spurious or these checkerboard structures or not. So in general, that will solve their problem. If you just increase these diffusion parameters, that will actually suppress this small scale grid size scale instabilities. But one has to also keep in mind that if you increase much more, your basic physics problem can be hampered, because some larger scale features can become very homogeneous due to increase of this diffusion parameter in a large factor. So and the next part is what I had to mention here, that writing auxiliary variables. So basically in pencil code, we deal with these parameters like log of density, velocity profile, vector potential, and entropy or temperature. So these are your basic variables. And what do I mean by auxiliary variables is that whatever variables which can be found from these four variables, let's say. So let's say I am to calculate the vorticity. Vorticity is curl of velocity field. So curl of velocity field, I know velocity field, but if I am to get vorticity, I have to do this curl operation. But if you see, if you are working with in a non-uniform grid, so there these derivative operations, if you want to calculate them as post processing, that those are like non-trivial tasks. So one can use pencil code for those things, and they can write these auxiliary variables like vorticity or like this current density Jj from vector potentials, which is like the 2 times derivative of A of vector potential. So one can write these auxiliary variables at the same time as their output, but they have to set some parameters. So let's say if you want to just write this current density, which is a vector field, has 3 components. Then you have to save, actually you have to save some space to write those data. So for that, you have to go to your cparam.local file. Here I have written, and you have to mention that how many auxiliary contribution you want to write. So for if you want to just write J, the current density, you have to set this n equals to 3. Or if you want to just write this J, this current density or vorticity both, then you have to set 6. because this 3 component of current density, 3 component of vorticity. So it will reserve some space to write these auxiliary variables as in your data. So with this, I'll just conclude. So here I have just sum up some few examples from this pool of samples. I would say that there are many samples. One can look at those samples. So these are like very basic samples. So you can check. You can start with like this 2D Kelvin-Helmholtz instability. Here is the path of that directory, which actually deals with this density contrast and velocity shear. So at interface, so there are interface above and below that interface. You have this density contrast and velocity contrast. So for that reason, there is this Kelvin-Helmholtz instability form. One can check this this setup like for solar. If one person is interested in this solar convection solar simulation, so one can check this one where this domain actually is from convection zone to corona, where these are the physics modules are included in here. LT is included, radiation is included, shock is included, semi-relativistic Boris correction is included. If one want to work with this corona solar corona module, so solar corona basically, so they can check this one where they have used this non-uniform grid and magnetograms as input, but here no radiation is included. And if one wants to check this MHD helical MHD part, one can use this path, and where the basic physics ingredients are like there are helical forcing and particles are also there. So those are like those could be like a good starting point to work with the pencil code. If you want to check this this interstellar medium, how this supernova energy injections are there, one can use this setup like this pencil code samples interstellar, where Coriolis force included, shocks are included, energy injections are included. So yeah, with this I am to stop. And the last thing I want to mention is that you can always check the readme file under every sample directory, where most of the references are there, and there are like short descriptions also. So that will give you some motivation or some hint that what that setup is deals with. Yeah, with this I am to stop here. Okay, thank you very much.
Thanks, Sahel, for the introduction. And if anyone has questions, doubts, they can just ask new users.
Or on the Slack channel or wherever. I mean, I think yeah, we will make this available, this video later on, and also the slides. So.
Yeah, it will be available in this.
I think next week sometime we will also have a demonstration session where we will show how to install the pencil code. And once you people have gone through the session, and then you can re-watch this video, then it will make a lot of sense. You can actually go in and make changes.
Right. Yeah. So on Tuesday, it is there. It will be given by Shambhiti. Okay.
Fine.